Okay, I should be recording. Hi, everybody. So this is going to be week 9, and we're going to get into diodes. And what I'm going to try to do while we're online here is I'm going to pull up my lecture notes, and these are posted on Eagle, so you can follow along with those or read them at your own pace. And I'm going to talk over them, and I'll try to write some annotations on the screen too, where it's appropriate, so it makes the material a little bit easier to digest. So I'm probably going to have a series of shorter videos to try to break it up and make it a little bit easier to go through, and we'll see how this goes. Okay, so we're going to talk about diodes, and we started to talk about this when we were discussing semiconductors before our midterm, which was a little bit of a while ago at this point, but hopefully you remember some of that. And our last lab, which was lab 5, involved wiring up that LED and taking some measurements. And we also wired up just a normal silicon diode and took some measurements. So hopefully you remember this diagram here, which is showing different ways that we can show a diode. So we have just showing it as a p-n junction. We have some p-type semiconductor material, some n-type semiconductor material, and then we have interesting things happening at this junction right here. So we can have current flow through in one direction, but not in the other direction. So a diode acts like a one-way valve for current flow. This is what the diode looks like physically. So we'll have a little cylinder type thing, and there's going to be a band that marks the n-type semiconductor material, and that matches up with the schematic symbol, and that would be the bar on the schematic symbol. Okay, so all those correspond to each other. Let's see if we can scroll down a little bit here. Oh, it keeps the annotations there. That's interesting. So I guess I'll have to clear those. All right. So we're going to get into starting to do some circuit analysis with diodes. And it's important to remember that these are solid state or semiconductor devices. So they're going to behave a lot differently than just resistors behave. And we've mainly just been dealing with resistors up until this point. What we use to analyze these components is a VI or an IV curve, depending on whether you have voltage on the horizontal or vertical axis. And that's just kind of a plot that we use to examine the workings of a component. So we can look at that for a resistor, which is a much simpler component, and then we can compare the response of a resistor to the response of a diode, for instance. So we can do this, we can make this plot looking at different values of voltage and current through a resistor. So this is actually something that we did way back at the beginning of the course. Let's say that we have a 1 kilo ohm resistor, and this would be assuming that you have like a little voltage source, and we just have this hooked up to one resistor. So we've got one 1 kilo ohm resistor hooked up to a voltage source, and this voltage source is variable. So it's going to have a bunch of different values. If we look at this axis right here, we've got values ranging from 0, going up 1, 2, 3, 4, 5, all the way up to 6 volts. Okay, so if we have, for instance, 3 volts, and we have, this is applied to our 1 kilo ohm resistor, we have some current that's flowing through it, and by Ohm's law, V equals IR. In this case, we're looking for I, so we'd be looking for this current. I is equal to V over R. And we have a voltage of 3 volts. This is the only component in the circuit, so that's going to be the voltage that's across that resistor. So we have 3 volts over 1 kilo ohm. So this is just going to be 3 milliamps, which is why we use nice values like 1 kilo ohm, because we can do a really simple calculation to get the current. Okay, so that's why we have milliamps labeling the current on this horizontal axis here. So this is going to create a very simple plot, right? So if we have 3 volts, we're going to get 3 milliamps of current. If we have 1 volt applied, we're going to get 1 milliamp of current. If we have 5 volts applied, we're going to get 5 milliamps of current. So we get this very nice, very linear plot for voltage and current through a resistor. So that kind of matches up with our understanding of resistors being linear components. We see a linear voltage and current response. Okay, so that's what we have for resistors, but we're going to see something that looks a lot different when we actually get to diodes. Okay, so if you remember some of the measurements that you took in Lab 5, you kind of got some results that looked a lot like this. So this would be your voltage source right here, Vs, and we were applying different voltages starting at very small voltage values, and then we were measuring the voltage across the resistor and the voltage across the diode, and also computing the current that was flowing through the whole circuit. So what we had here for our circuit was our voltage source, which we were changing over time. Then we had a resistor, which was again a 1 kilo ohm, so we could have an easy current calculation. This would be the voltage that we measure across that resistor, and then this would be our diode. Okay, so then we have our voltage across that diode as well, VD. And then through this whole circuit, because everything is connected in series, we have the same current, which is I. And then how we found that current was by taking the voltage across this resistor, dividing by the resistor value. So it would be VR over 1 kilo ohm, which is that resistor value. So we would get whatever that voltage value is, the number of that in milliamps, because we're dividing by 1 kilo ohm. Okay, so we started off with a very small voltage value, 0.2 volts, and then you're going to see all of that dropped across the diode, because what you're going to have below a certain voltage, this is going to act like an open circuit. So if you've got this very small voltage, this 0.2 volts, got that resistor, this is acting like there's no connection. There's no connection. It's basically a very, very high resistance. You can't have any current flow in an open circuit because there's just no physical connection between those 2 points. And this diode at a low voltage is acting like there's no connection. So if we have that no connection and this very, very high resistance, higher resistance means more voltage is dropped across that point. So we would have all of this voltage that's applied dropped across that open circuit. And that would actually be, for our circuit here, we would see that whole voltage applied dropped across the diode. Okay, so it's acting like an open circuit at this point, no current flow, so we're going to see 0 current. And that's going to pretty much continue up until we get to 0.5, 0.7, 0.8 volts here. So we're going to start to see a little bit of a trickle of current, but nothing really significant until we get to this about 0.7 volts mark. Okay, so we're going to see more voltage across this diode and also some voltage across this resistor, because now we have some current flow. Also, if you add up these two, the voltage across the resistor and voltage across the diode, you would have to get the voltage supplied, because that's just Kirchhoff's voltage law. So the sum of all the drops in that circuit have to equal whatever is supplied. So we can pick any values here. For instance, this one right here, if you've got for VR 0.43 volts and you add that to 0.57 volts, you would get 1 volt, and that is equal to the supplied voltage. So We can just double check using Kirchhoff's voltage law if we want to. Okay, so what we should notice here is that as we increase this voltage source, this is going up, and we're getting larger and larger values for that, the diode voltage is going to slowly increase, but then it's going to hold steady around 0.6, 0.7 volts. And we're seeing that here. We go all the way up to 6 volts, and this is still only at 0.7 volts. So we're dropping more voltage across this resistor to compensate because this diode voltage is not increasing linearly. It's going to increase up to a certain point, and then it's going to hold steady, basically no matter what voltage you apply with a voltage source. So if we try to plot that, we'll see what that looks like. Get out of annotation mode. So this is what that plot looks like. We have the current through the diode, which is increasing if we look at this table that we have up here. And we have the voltage across the diode. And that's going to start off very small because we had very small voltage applied using the voltage source. But eventually, it's going to level off when we get to this about 0.7 volts for a silicon diode. And that's going to hold steady, but the current through the diode can keep increasing. So that's why we have this graph that's going up once we reach that certain voltage. Okay, so that's definitely not a linear graph, and that doesn't look like our response for a resistor. So these are some very different components. Okay, so I'm just going to pause the video here for that, and then I'll continue on in the next one.